Hello guys, welcome to another episode of Xa Talk Show. Today we are going to code Wolfram language. We are going to continue Advent of Code 2023, Day 14, Part 2, which we did 3 days ago about. So we're going to continue explore that problem. But you don't have to watch the previous episode because today we're gonna do independent. I'm gonna explain the problem. It's pretty short. I mean, easy to understand problem. So we're gonna explore and see what is going on with this problem. This, the Advent of Code 2023, Day 14, Part 2. It's fairly, it's kind of more complex, difficult problem. Okay, so welcome all. If you are watching offline, skip around because I ramble and I talk slowly. I ramble a lot. Skip around and play at speed 1.5. I think 1.5 is optimal. And then preferably you sit in front of the computer, you skip around, like every 5 seconds. If you are watching online, live, say hi. Okay, so we're gonna start to code this. So video check, audio check. My keyboard's Ultimate Hacking Keyboard, that's this one. This is Glove 80. I have video reviews on YouTube, and this fantastic, this is called Data Hand. Svalboard, Svalboard. I also have a review, but I'm not ready to use it yet. Okay, sorry about that. So let's begin coding. Okay, so the problem is you are given this. Let's start Wolfram language. Okay, now if you don't know yet, search for Xa Wolfram language. You'll see the download link and the tutorial for programmers. Okay. So here's the problem. So the problem is that you got this text, okay? You got this, given text. This O, capital O, they represent a ball, a marble, okay? So consider this is a board, like a wooden board. So this O is a marble, and these dots are empty spaces. And these pound signs are pegs or wall. Okay, so these pound signs, they are immovable. They are just walls. So these marbles can roll around. They can roll to any of these positions of the dots. Okay, so the problem is that you're gonna tilt the board. So there are 4 directions: north, west, south, and east. So when you tilt the board north, all the marbles will roll to the north. So for example, this O will become at that position. And this O will move over here, then stop by the wall. And for example, this O will move over here, stopped by the wall. So that's when you tilt north. All the balls move to the north. Okay. Then similarly, when you tilt west, all the zeros, the O moves to the west. So this O will end up here. Does that make sense? If you are here, say hi. Hi, Alejandro. Finally on time for stream. Thank you. So check video, check audio, check. So that's when you tilt west. Then when you tilt south, similarly, all the O move to the south position. For example, this one will end up there. Then there's a tilt eastward, similar thing. So the problem is that you're gonna tilt the board north first, then west, then south, then east, in this order. Okay, every time you tilt, all the balls move to that direction. Then you tilt north. Starting with north, then west and south and east in that order. Okay. Now, once you do this is called one cycle according to the problem specification. So you do this, so one cycle. Then the problem says you have to do this 1 billion times, 1 followed by 90. So you have to do this 1 billion times. Okay, that is a problem. So what exactly is the problem? Is the answer? What is the question? The question is, once you done this 1 billion times, basically you want to count in each row the number of balls in each row. Then for each row you have the number of balls, then you multiply that row by the reverse count of the index of the row. So if there are 10 rows total, and the first row will have a weight of 10 multiplied by 10. The second row multiply the number of balls multiplied by 9. The third row, the number of balls multiplied by 8. So you multiply each total count of number of balls in that row by the inverse of the row number. Okay, then you sum it up, then that is supposed to be the answer. So you have to do this, tilt them north, west, south, east. That's one cycle. Do this 1 billion times. Then count the number of balls, multiply by their weight, and sum it up. That is the problem. Advent of Code 2023, Day 14, Part 2. Okay. Now the problem, okay, so we explained the problem specification. Now the problem is that, so we have a solution, we did code the solution. Okay, so let's show in Wolfram language. So the solution is just, so we begin with, this text input. Okay, then this part is personal input, it's much bigger, but let's skip it now. Then we have my solution is, turn it into a matrix, then do this replace all. Okay, so instead of using, this string O and string dot and string pound, I change them to 0 and 1 and 3. This step is not necessary, but but you do that, it's easier to manipulate, so you deal with numbers instead of strings. But anyway, this step is not necessary. So then you get the row count, total row count, then you get column count, which actually we don't need. But anyway, this is a solution for last time. And here is a function to cycle them. So if you want to understand the detail, watch the 3 days ago or last week. We have full explanation. That video turns out to be 3 hours. Okay, then you just call this F1 cycle, which cycle them one time. You're supposed to call them 1 billion times. Okay, then you just total, like count the number of balls in each row, then multiply by their inverse of the index, then total them. Then that's the answer. Okay, so if we run this, okay, so this part, actually remove it. Okay, delete it. You see, if we run this, right now we are just running at 10 raised to the power of 2 times, which is just 100 times. If we run it, shift enter, so here's the result, and the solution, the answer is 68. Very good. But now the problem is asking you have to do it 1 billion times. That is a problem, because if you run just 1,000 times, then it will take like 11 seconds. Okay, so 1 billion times is gonna take days, or what was it, years, I forgot. So the problem today is we're gonna continue to do this and see where exactly, how to solve this. Is there's some inefficient code somewhere, or is it because we need to find some kind of shortcut? We are going to explore this problem. Okay, so you see right now it's trying to do 1,000 times, 10,000 times, and it's still running. So this is not gonna work. Okay, so that is the situation. Okay, and then today we're gonna just explore this problem systematically from the ground up. So okay, let's get warmed up. Let's see. So let's break this function. So let me explain them one by one. Okay. So actually put them back. Okay, so let's start a new Wolfram language code, paste it there, and pop it out. Okay, so this function fcycle is defined by by 4 components. So you have move north, which is represented by that function. Represented by this function. Okay, let's move north, then move west, then move south, then move east. Okay, so you have 4 functions. Now, let's decompose these 4 functions into each one of them. Okay, so let's do that. Okay, let's just let me just code it so you can see. So let's define north. Okay, so move north. Okay, so that's one function, and let's just let me just so we don't need this. So let's see. So this should be one function. You see, so okay, let's move north. I'm gonna explain how it works in a bit. Then move, so now you need move west. Okay, equals to, you see the code is it now. The code is finally done. 69. It takes like 10 seconds or something. So anyway, now move west is a function. That's right. Okay, put a semicolon there so that it doesn't show the result. It kind of suppressed the output. So move west and then move south. Okay, so constant equals to then this function. Now the function, the keyword function in Wolfram language basically is like lambda in Python, in Lisp, okay, or in JavaScript, just function. So here's a function, and here's a parameter xx. Then this is what you do. The second argument to the function is the definition of the body. This is what you do to the parameter xx. Okay, so semicolon, then move east. Okay, so we're gonna define a move east, a constant equals to this function. Okay, now how does this work? Let me quickly explain this move west function. So to move all the 0, so you see we changed the O to 0, and we changed the dot to 1. Dot is spaces, so we changed the pound sign to 3. So we work with numbers, kind of more familiar, instead of like strings of single character. First of all, we turned the problem, a string, a giant string, into basically a matrix. Okay, so the ones are just empty space. 3 is a wall, and 0 is the balls. Okay, so for example, to move all the zeros to the west means that you want to move 0. If there's a 1 in front, move it to the left. So you want to move 0 all to the left. So let's try it. For example, because now we have nicely defined each individual functions, 4 of them. Okay, so let's so then we don't need this part anymore. Okay, so we just got these 4 functions. Cut them, show them in Wolfram Notepad, so you got more nicely color, syntax colored. You define 4 functions. Okay, so move west, how does it work? You see, so you got a function, and the function has two arguments. The first argument is just it's just the parameter names, and the second part is just replace repeated. We use a pattern matching. So replace repeated means that given an expression xx, what you do is you find this pattern. This pattern is a list. It begins with 0 or more something, then followed by a pattern named dots, and this pattern is the longest match of 1 followed by 1 or more. So 1 or more ones. So like that longest match. So this pattern, so you want to capture all the ones because the ones are like space. You call it dots. Then followed by a pattern which is named by balls. Then it's longest sequence of zeros, 1 or more zeros. That's represented by this pattern. Then followed by tail. Tail is like 3 triple low line, which means 0 or more things. Okay, and the whole thing is in the curly braces. That means it's a list. So when you see this pattern, then right arrow means change it to this head, balls, dots, tail. So you basically just swap the positions of the balls and dots. You see, the dots and balls, they are the names for the pattern. So once you capture this pattern, you are giving it a name, dots. That's how this works. Similarly, the head is just a name for this 0 or more. Okay, so you for the x expression xx, you find this pattern, then you replace by this. Okay, and you do it repeatedly until the result no longer changes. That's what this replace repeated does. Okay, so this function, that's how you move all the balls to the west. Now, similarly for the east, you just swap the positions of the dots and ball. Now, for north and south, basically what you do first is you transpose the matrix. Transposition means like flipped it around a diagonal, left to bottom, upper left to bottom right diagonal. You flipped it. Then you do the move to the left. Then you transpose again. So you need 2 transpose. You can see there's transpose. You transpose it, then you match the pattern to the move all the balls to the left. Then you transpose the result back. So that's how you move things to the north. So this is kind of a different approach. This is in Wolfram language using pattern matching. Okay, does that make sense? So we got Steve is okay. Steve got something to say. We are arguing about functional programming and OOP. Anyway, so we need to focus on this problem. So cut this and put it back, and let's modify our code. So we somewhere we define this function F1 cycle. Now we paste these 4 definition functions, move north, west, south, and move east. So now we redefine the F1 cycle, like to do the sequence of them, by simply calling each one of the above. So you don't so that we can start to modify. So let's see. Let me show you. Okay. So actually you need a function. Okay. So function. Let's say the input is yy. So what you do is that, so actually we don't need the rest. Let's just delete it. Okay, so we define the F1 cycle by parameter yy, then expression is yy is the argument, then postfix notation, what is the character here, okay? So that // is equivalent to the Unix vertical pipe, okay? So you pass the argument YY to move north, okay? Then you, okay, so then you move west, then you move south, then you move east. Okay, so let's see. Make that one line so it's kind of nice. So again, double check. Given an argument, you pass it to move north, then result path to move west, then result path to move south and east. Okay, sounds good. Okay, now given this function, now we can actually test this again. So copy all. Now previously, you see, previously when we do it 100 times, let's say 100 times, shift enter, run it, the answer is 68. Okay, now let's copy all, select all, paste. Wait, let's do, so yeah, so let's say 100. Okay, and let's remove this part. This part are just duplicate of the above. Okay, so copy all, select all, paste. Okay, here's the code in Wolfram language. Now shift enter, run it. So you see 68 is basically the same result as above. Okay, but now that we have decomposed the function, we can call each one at each one and see exactly how they change the board configuration. Okay, so the input, okay, this big matrix, this is annoying, this personal input, let's remove them. Okay, so so delete so we don't. Okay, now it's short. Okay, let's shrink a little bit. Is the font size too big or what? Can we do smaller like that? Okay, so you see X matrix is our matrix. Okay, so let's just run it. I mean, doesn't matter. Okay, so shift enter. Okay, let's shrink this a little bit so that matrix shows as matrix there. So X matrix, shift enter, that's a matrix. Then you call move north. Okay, and see, you can kind of see. Okay, with with numbers it's actually harder to see. Yeah, with numbers it's not harder to see, so let's change it back to string. Okay, let's not have that. Okay, so let's not do this. Use numbers. Okay, let's not use numbers, let's just work with string. So to work with string, so 0, replace all 0 by a string of capital O. Okay, do it. Okay, no, do it there. Okay, now replace all 1 by dot. 1 is dot. Okay, not there, no. Okay, and then there's one more replacement. So replace all number 3 by the pound sign. wait, oh, okay, it doesn't occur, that's okay. So copy all back to Wolfram language, select all, paste, and run the code. Great. So let's see, matrix, X matrix, run it. Okay, now we can show, now there's a comma there, which is annoying. So let's kind of show in matrix form so that it will hide the comma. So now it's easier to see. Okay, so now we do the same now, except now let's apply move to north. Okay, shift enter. So now you can easily see, you see this 0 right here is moved all the way there. Okay, so you can see all the balls got moved to north. Now let's do another one. Let's move west. Okay, north and west. So for example, this will be over here. Let's do it. Exactly. So this way we can visually see our program is working. You see, so this 0 is now here. That's correct. Now let's see. So the next thing we want to check, the problem is, we want to find out what actually happens when you move northwest, southeast after one cycle. How does it affect? So let's try. Okay, so next, so let's just do this fast. Okay, I mean, let's become more advanced. So before we do that, let's do same thing like before, but this time we do the cycle, F1 cycle. Okay, so shift enter. So this is after moving north, west, south, and east. Okay, so here is the result. Now let's see what is the effect if you do this again. Okay, so F1 cycle, then you do it again, F1 cycle, shift enter. Let's see if there's any difference. There is indeed. You see there are 4 zeros there. Now it's only 3. Why? Because we can try to trace it. You see, first you move all these 4 north. So you can, so let's try something fancy. Okay, so let's see, how do we do this? What we want to do is we want to see the effect, preferably visually, how this ball moves, and what is the effect of repeating a cycle. You see, here's a difference between two cycles, but it's, we can see they are different, but we are missing each individual steps of tilting the ball northwest, south, east. Do I make sense? Okay, so what do you want to do? So what you can do, you can kind of do an animation, interactive animation of this board. So in the animation, what you want to do is you want to move them north, west, south, east. Okay, north, west, south, east. Then north, west, south, east. Okay, so northwest, southeast. Okay, then northwest, southeast. So you kind of have this. Let's just explore. Okay, so let me just show you what. Okay, move back, make a backup, pop out, and let's do this. Okay, move north. Let's create a list of moves, something like that. Equals to is that. Move north, west, move south, then move east. Okay, that's one thing. And we want, I'm just hacking, so we want, like a list like that. So north, west, south, east. Okay, so we want some kind of animation sequence nest. So you want to use fold each time takes that, then takes more, then takes more, then takes more, then takes that. Okay, so I think I know what to do. So you want, so let me show you. Okay, so you want table. Okay, take list of moves, each time take X number of them. Take just return from the first element to nth. Okay, the first n elements, that's what take does. Tab H show you the documentation. Okay, so yeah, good. Control magnify. Okay, so that's, take the first n, but God, what's going on? Clear. Okay, so now, but X goes from 1 to, let's see, what number? 2, 3, 4, 5, 6. Let's say 24. 24. Okay. Let's say, 4 times by 5. Okay, so we got 20 steps. So, but what do you do with the list? So once you got the list, so we can run this, so we can show it. Oh, each one. Okay, each one is a function. Wait. Yeah, each one, they become a function. Yeah, but yeah, so each one, these are functions. That's correct. Wait, did I define them? Did I define them? Yeah, well, we define them as functions. Okay. Yeah, but okay, so this is not, well, it's preferable to not show the function instead of just show the function names. Okay, but let's ignore it for now, okay? But anyway, yeah, but then you cannot see the structure of this table. Okay, so wait, so this needs to be, wait, did we do it correctly? Shift enter. Yeah, it works, but now each one of these is a function. They show up as a function. So, okay. So what we have to do now, hello Plash, great to see you. So now what we have to do now is to, Plash, are you the guy? Are you the Indian guy from XR Discord? I'm wondering. So anyway, so focus, okay? So we got a list of, function names. What do you want to do? One thing we can do easily is we can hold. Yeah, okay. So again, if you are watching offline, just skip around, okay? So I'm just gonna go easy. So let's see. So so once you have that, you want to, so what do you do with the list? So what you do is okay, let's just, forget about showing symbols. So for this, you copy that, paste it. Okay, let's put it here. So what you do is, once you have this thing, this is a sequence starting with one element, then two elements, and then three, which is just a bunch of this list. You fold, you call the fold function. Fold is like reduce in Python or others, okay? You call the fold function, you apply a function. First argument is a function, the second argument is a list, and in our case is that list. So what function you want to call? You want to call, and then you need the argument. So the argument is X matrix, okay? That's the input. But what is the function you want to call? Okay, you need to construct a function. So let's do it here. So it's a function. This X is one of these functions. Okay, so this getting into kind of advanced functional programming. So let me just do it. So X is a function. You want to apply it to, wait. So yeah, X is the argument. So this function needs to take two arguments, X and Y, okay? And what is the body of the function? Well, the body of the function, so it takes two things. X is originally this matrix, okay? So so let me just, and Y is actually the function from this list. So why is that? So why don't we rename them so that it makes more sense? Okay, so fold, the first fold is reduce. So it takes a function, takes two arguments, three. The first one is a function, the second one is the initial input, the third one is a list. Okay, so what the function do? The function will take two arguments, we name it arg and ff. So, and it will return ff applied to arg. Okay, yeah. So this, so we don't remove that. So this is what we want. Okay, so okay, so actually, so this is getting slightly complicated. So anyway, but you'll see the result. Okay, now we don't want that semicolon. Okay, So now let's paste this code. Okay, run it. It will give us a sequence of this northwest, southeast, then northwest, southeast sequence of them visually. Run it. Indeed. So you can see now, but we need to put them into a matrix form so it's easier to read. So let's, so that would be here, okay? So we actually, so let's put it here. So postfix notation, matrix form, okay? Shift enter to run it. Great. So you can see, oh, we got an error, oh. Yeah, well, that's a problem with the matrix form, because if you call matrix form, it became part of the expression. So then when you do, when you call the function on the matrix, it didn't get the matrix, but it gets the matrix form of the matrix. So it doesn't know what to do. So that's why you got this transpose, So you need to remove the matrix form here. Instead, you want to apply the matrix form to the whole. Okay, so let me show you. So that this is what we want. We want to map, okay, map matrix form a function to this thing, okay. So let's name this thing by board history. Okay, not board move history, something. Okay, board history. So board history is a list of matrices of movements. Then you just say map the matrix form to the board history. Okay, good. We don't need that. Okay, so that okay. So put a semicolon there. So there. Okay, so control dot to select, then paste. Okay, shift enter. Fantastic. Yep, fantastic. Okay, so you can see in the beginning we got the matrix all moved to the north, then to the west, then to the south, check correct, then to the east, check correct. Are they all on to the east? Yes. Then north again, check. Now you see, now this result is different from that result, so when you do an extra cycle, it became different. So this is north, then west, seems correct, then south, then south, is that correct? Yes. Then east, is that correct? Yes. Then north again, that. Now, is this north same as the before? No, it's different. I think that was north. So anyway, so that north, then west, then south, check, seems right, then east, okay, then north again. Okay, now let's remember this pattern, because let's see when is it different. So 0 0, then gap pound dot 0 0. On the right side you have a vertical zeros on the right, and in the middle, wait, this is north, right? Okay, so in the middle you got this kind of configuration, like a human crawling or something. Okay, so this is north, west, south, east. Okay, then north again. Okay, now it looks like the same. No, Okay, notice here you got this configuration. The right hand side 4 lines got connected to the left columns, but not over here. See? So you can see the cycle differs. Okay, so then north, west, south, east. Okay, that is actually the end. So what have we learned? We learned, so when you move every north, west, south, east, every cycle, the result is actually different. So the question is, when will the result be the same? Because when it's the same, when you are sure that every time you do a cycle, the result no longer changes, then you can stop. Okay, and maybe that's the key to solve this problem, because you need to do this cycle 1 billion times. Hello, Joman. Hey, haven't seen you for a while. Joman is a Wolfram language coder. Okay, so what I want to do, we are doing kind of trial and error to visualize this problem. This is a very good problem for visualization, because you are seeing the balls move on the board. And but if you really want to solve the problem, you really actually you need to think about this problem like mathematically as a puzzle. That is a real way to solve the problem. As a mathematician, you want to analyze what happens to the balls. But we are doing, using computer to help us, kind of. But it's not the true solution. It's not the true way to solve mathematical problems, because for real mathematical problems, you don't want just to trial and error and see what happens. It helps a bit, but that's not the ultimate approach, because if you do this trial and error, it can it can end up many hours. You don't know what's going on. Just like trial and error programming, which you shouldn't do. But anyway, we are exploring the Wolfram language. So anyway, we see the visual pattern, but what I want to do is more another trick in Wolfram language is that you can do the whole thing by, let me show you, by a more better visual approach. Okay, so what you do is, let me just code it. Okay. Wait. Okay, so we got, so what is this? Map board history, matrix form. Okay, so okay, manipulate. Okay, board history. So we want to do manipulate. Manipulate is a way to show animation step by step, which is a very powerful, useful Wolfram language thing. You don't have that in any other language. Okay, so manipulate takes, just like a table, takes 2 arguments. Okay, so the first argument is going to be this board history. It's a list. Okay, but we want to take the nth element. Okay, then n goes from 1 to 24. There are total 24. Okay, let's do this. So, and actually you need the matrix form. Okay, so that, paste, shift, enter, So that's what we want. This is beautiful. Now we can, so we can go step by step. Let's see. Right arrow. No. Click on that. Oh, we got what? Okay. This is not what we want. Wait. History, manipulate board history and matrix form. So when n is 1, when n is 2, okay, what's going on? Okay, let's see the documentation. Expression u min u max. Generate a version of expression with control added to allow interactive. Okay, instead of, okay, maybe we want to say instead step of 1. Okay, let's try that again. Shift enter. Yeah, okay, because before it's 1, it's going into real numbers. Okay, now it's good. So this part we don't want. That's a mistake. Oh, that's a board history. Okay, so now we got this. Next, let's see. Wait. Oh, this one. Step forward. What? Can you use arrow? I want to use arrow key to control. Okay, we still got an error somewhere. 11, 12, 16, 18, 19, 21. Wait, something is wrong. So how many total things we have here? Oh, we got 20 things. Okay, so actually let's make it more beautiful. Okay, let me show you how to generate a more elegant way to generate this sequence of 4 things. Okay, so instead of hard coding this like that, you just have them one thing, one thing. Then you use a table. Okay, you want a table of this thing, and how many times? Let's say 10. Okay, so you don't need x 10. Let's see if that works. Yeah, okay, so okay, let's hold. So hold means don't evaluate. Okay, so hold. Okay, let's do that. Hold, hold, hold. Okay, so make it easier to read. So that so you got okay, actually don't, I mean use hold form instead. Okay, so that's what we want. Then you need to flatten it because now it's nested. Let's see, do I want to flatten it? Yes. Okay, so now you just say flatten add. Add is a prefix notation, so when you have some symbol add something, that basically just means that. Okay, so these two are equivalent. For example, let me show you, because Wolfram language is symbolic. You see, when you run this, Wolfram language doesn't know what is FFFF or what is XX. They are just symbols. So, but this is a shortcut for this, so it just become, it's the same thing. It's exactly the same thing. So that's why we are using add here. So the advantage is that you avoid, lots of nesting of the brackets. So, okay, so remove that. So, and here we use flatten add this whole table. Okay, so this thing we can now do it. Okay, so that's beautiful. So Lisa moves, so now, much shorter code, elegant code than this, than that. Plus we hold the form, so all these functions, they don't become the function body itself. Okay, so that's list the moves, but once you make, now each one is a hold form, you have to say release hold. So this FF, you need to say release hold, because otherwise it won't work. Let me show you. So otherwise, if you say that, it just okay, remove the semicolon, run it. You see, it just shows that because that function you told it to hold, so it's not actually applying. So you have to say release hold here. Okay, release hold. I'm not sure. Maybe you need a paren. Oh, it works. Okay, so let's see the precedence. Yeah, it works. Okay, so you need the release hold here. So fantastic. Okay, so now here, let's try this again. Board history. Now board history, what history? Let's define number of cycles. Okay, equals to equal how many cycles? Let's say 10. Okay, so number of cycles is 10, and let's just put it there. Then this will be number of cycles. Okay, yeah, so let's try it again. Do it. Run it. That's good. Then here is the board history. Let's double check board history. Run it. Paste. Run it. Yeah, we got that's one matrix. That's the second matrix. That's right. So that's a board history. Then you map matrix form to board history. Okay, we are going too slow. Then you manipulate and manipulate, then number of cycles. Okay, so number of cycles times 4. Okay, yeah, do it. Fantastic. Now let's expand play. We still got problems. Oh, we forgot you need to say in increment of 1, not getting into decimal stuff. Do it. Fantastic. Play and slower. Oh, now it's beautiful. Slower, slower, slower. Okay, now let's see. So we got 10 cycles. 1, 2, 3, 4. Yeah, so fantastic. This is a great achievement for today's talk show. Are you guys seeing this? Wolfram language, you can do this. Of course, you can do this in Python or even Emac Lisp. You can just generate the text and play the text. It's fun. But Wolfram language lets you do this much easier. Okay, so now let's look at this. What's going on with these marbles? South, east, north, west, south, east, north, west, south, east, north, west, south, east, north. Yeah, that's fun, but it's not actually solving the problem. We need to stop. So we need to actually think about what's going on. Now, can you use arrow keys? Let's see. Play. Now, back. Can you use arrow keys? No, but I think you can. But you need to do something. Yeah, so I have to look up on how do you map the arrow keys to make them go forward or backward. So, but anyway, so here is the thing. So, okay, so now we need to think what's going on with this puzzle. Am I doing good? Are you guys following? Hello, Huang. Oh, Jorman caught my error. Thank you. So what is going on with this problem? We need to do this 1 billion cycles, 1 followed by 9 zeros. And so actually the real question we want to know is, we want to know what happens in each cycle. When does the cycle no longer have an effect? So, you really need to think about this problem. Because for each cycle, there are 4 tilts, north, northwest, southeast. So each cycle is actually made up of 4 steps. Yeah, so you really need to, I really need to start to draw, to think about what is the effect. When does the tilting no longer change after a cycle? So anyone? But don't give me the answer yet. Okay, Steve has solved the problem, so he's warning me about the issue, but I don't want to look at the spoilers yet. So yeah, so okay, so right now actually I just need to think. Okay, so here is the whole code, so you can see. Let's maybe clean up the code. Number of cycles, sport history, and Yeah, so this is only 10 cycles. Select all. Yeah, select all, paste. Okay, here's the whole code. Shift enter. Let's rerun it and generate the board history. Then you got this animation. Play it. Okay. Okay, it's already 1 hour. Should we want, and I'm not anywhere yet. So far I've been just playing with the Wolfram language, but not actually solving the problem. Okay, so you move them. So what about, you just call a fixed point so that it will know when the cycle no longer has any effect, then it stops. But I tried that yesterday. That doesn't work. It still takes a long time. So I don't know why. But so really what you really need to know is actually what happens to the marbles, as a math problem. And I don't know what to do now. So okay, let me just think about it. We can, so far so good. We kind of played with Wolfram language and we got into this visualization. It's very good. But this visualization helps, but does not obviously answer when the cycles no longer have effect. So to really solve the problem, you really just need to think about that. And if I do that, then it's gonna be me just sitting here thinking for 10 minutes. So there will be no video content. So what to do? So I don't know. Okay, so maybe we can try to think about this problem, while I walk, draw some pictures or something. Juan says, I'm implementing programming language following a book called Crafting Interpreters. Yes, I think we talked about that. Someone posted that, I think, or was it? Yeah, because I remember I was just reading about that a few days ago. Good for you, but yeah, that came from, so there is this book called Crafting Interpreters, and which allows you, oh yeah, that came from, but anyway, there's a book about crafting interpreters. It's also free, or you can pay for it, but it's also free online. Supposedly a great book which teaches you about designing and implementing a programming language in whole from the ground up. So you have to, now I don't know to what degree it actually teaches you about designing a language, but however, it does teach you about, implementing, kind of implementing a language from the ground up, including, writing a parser, writing a compiler. So anyway, so supposedly that's a good book. Yeah. Anyway, so going back to this problem. we want to know when does its cycles has no effects. So the other thing we want to know, which is slightly separate, is that why does fixed point not work? Because if you know, every time you do this cycle, you can tell Wolfram language to use, you know, you call the fixed point function, which just repeat this until the result no longer changes. So that should be a solution, assuming that the cycle will have no effect at some point. So you don't have to do this a million times. As soon as the cycle stops having any effect, the program stops. So you save a lot, you know, redundant computation. But like I said, I tried it yesterday, or today, you know, a day ago. It doesn't stop right away. So, but I haven't thought about why. So one question is, why does the fixed point does not seems to work? That's one thing. Maybe it actually work, but it's just because our code is not efficient, so we are still have to wait a long time. So that's one question we can pursue. But the central question is really actually the math problem. What happens to the balls? Okay, let's think about what happens to the balls. So, well, I mean, in order to do that, it's just mostly just about thinking, okay? So, but let me try to do this interactively. So think and explain what my brain is doing. Okay, so we kind of, so given a board, so you know, you got these marbles. When you tilt north, they go to the north. Okay, so you tilt west, south, east, the ball rolls. They keep rolling, but what is a condition that for each cycle the balls no longer moves, no longer change? You see, in between a cycle, you know, every time you tilt northwest, southeast, they will move almost all the time, because, as you know, the only condition that when you tilt, nobody, you know, no balls move is when the balls got walls on all sides. So when you tilt north, and if the balls are already tilted north before, then there's no change. Okay, that's, you know, that's one condition. Then when you tilt west, the ball will not move only when the ball are all kind of has a western wall already, or in other words, you already tilted west before. So the condition for each tilt, the condition that the ball do not move at all, no balls move, is when the balls already have a, you know, a wall in that direction. Okay, but now, however, when you combine the tilting in different directions, northwest, southeast, you see, it is possible that after this cycle, the ball will not move at all. But however, when you tilt in each direction, the balls move. They will just, after all the direction, they just come back to the original position. So when does that happen? For example, it happens when you have like, let's see, a wall there. Here's a ball. Let's see, you know, for example, this is one I can think of. You know, so let's say a line here. So here is a wall. And here's a wall, so you have some kind of swastika pattern here, okay? So this ball, when you tilt north, it stops here. Then west stops here. South, it stops here. Then east stops here. Oh wait, Oh, gotcha. Wait. Oh, so the end step is east, not north. You see, then you move north, then it stops there. So, oh, I think I know the answer. Fucking tricky. Miraculously, I wasn't planning to really solve it, but this is a simple example to see how the ball stops moving. You see, in this case, it will stop moving because every time you do a cycle, but you see, it stops moving only if you try to move north again. Then the ball doesn't change. You see? You see? Yes, I see. So now actually I do know the solution. The solution is to use a fixed point, but however, the ending segment is not when, you see, the end is when the ball are tilted to the east, but what you want to actually check is then you move to the north and check. Okay, so I think I know the answer. Jorman says, is this related to cellular automation? No, not obviously. Not in any obvious way. But I presume you can turn it into a cellular automation, though. Yeah, I mean that would be a different thing to explore. To turn this problem to specify this problem in terms of cellular automata, because cellular automata is also dealing with grid, cells, and you have rules that govern each generation where the different conditions of the cells are. So in terms of cellular automata, you have a grid 10 by 10 in our case. Wait, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, 10 by 10. Then each cell has 3 conditions, either O or dot or pound sign, right? And then you have a rule to determine in each generation what the cell changes. Okay, and that rule will be very difficult to specify. For one thing, if the cell is already a pound sign, that cell never changes, okay? But if the cell is a period, that cell will change depending on, it will depend on the neighboring periods and all. So to specify this as a cellular automata, the rules will be quite involved because it will involve kind of all the adjacent vertical or horizontal, as long as they are dots or 0. Yeah, so so the rule for each generation will be fairly elaborate, and it will be kind of like our code of using this, using the pattern matching. So the rule will be fairly complex. But what benefit do you get if you think of this problem as cellular automata? What benefit would you get? I'm not sure what benefit you would get. So, yeah, that's interesting though. Anyway, so I think I know the answer. Let's, why not we try to, solve this advent of code problem. So the answer, so we can observe this situation, so the cycle will stop yeah, only if you compare. Let's see, 1, 2, 3, 4. Wait, how does that? 1, 2, 3, 4. So each cycle is 1, 2, 3, 4, 4 tilts. 1, 2, 3, 4. And you want to compare, so given the beginning, 1, 2, 3, 4. Wait. The end is always moving to the east. Okay, the last tilt is always moving to the east. So the ball would be here. Okay. 1, 2, 3, 4. Okay, end on the east. Then yeah, so if you use fixed point, it should still work. 1, 2, 3, 4. 1, 2, 3, 4. Right. So the end condition. Let's go back for just see. 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Let's look at this. Okay. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Slow down. Slow down. Slow down. 1, 2, 3, 4. 1, 2, 3. Let's slow down. Slow down. 2, 3, and slow down. 4. 1, 2, 3, 4. Check. 1, 2, 3, 4. Stop. Check. 1, 2, 3, 4. 1. Okay, let's just observe this for a while. I still don't get it. 1, 2, 3, 4. North, west, south, east. North, west, south, east. North, west, south, east. Oh, different, This is so interesting, getting interesting. So let's increase the number of count. Let's see, let's increase the number of cycles. Let's say 10 cycles, let's say 30, okay? And then let's put a semicolon so it doesn't show it. Copy all, select all, paste, run it. So 30 cycles. Okay, this is only 30 cycles. Let's magnify. Okay, and run this. Okay, too fast. Slow down. 2, 3. So what I'm trying to observe is the lower right corner. So try to observe the lower right corner configuration changes. Okay, let's start from weighted to finish. North, west, south, east. North, west, south, east. North, west, south, east. North, west, south, east. North, west. Oh, they changes. Okay, so okay, I got new, so I started to have a new idea. So we are observing, I am observing this corner, okay, the lower right corner. So you see, for part of the board, the configuration may repeat after a certain cycle. Okay, but however, for other part of the board, the cycle do not sync. So each part of the board, they may repeat after, each cycle, after certain cycles, then they repeat. But the period may not be the same. The period of each local regional repetition may not be the same. So yes, but what you really want is you want to find the periodicity of the entire cycle repetition. This this is really interesting. So let's look at this again. Lower right corner, but it still doesn't explain why fixed point won't work. Am I making sense? Let's see. So look at this part. That. Okay, so you see, it ends up in this configuration there. You see this, but however, you see now that pattern is gone. You see now it's gone. So there, okay, after 14th cycle, 14. There, 20, 21. There, 25. 3, 4. There, 29. 2, 3, 4. There, 33. So, but in 37 it becomes something else. What? Okay, let's start from the beginning, okay? Start from the beginning, do it again. North, okay, there. 3, 21, okay, 21, 25, 29. You see, you got this field pattern there. There, but now it's missing here. You see, now it's missing. So they mutate into a different stable pattern. Okay, now it's 4 zeros here. That's again different. You see, okay, 27. Okay, now it's missing a 0 here. Okay, so then it came back to that pattern. You see, so what does this mean? So actually still we don't know the answer to this question. So okay, but maybe I stop though. So let's see. The Hello Sally Well says, "I'm a bit sad today. Your talk show make me feel better. Thank you." Okay, so far we don't know what's going on. Why? But you see the whole pattern, if the cycle has no effect, it will go into a period, right? A periodicity. North, west, south, east. Okay, so now let's stop this. Now I got a better idea. Now this animation is showing each individual tilt. Okay, now let's try to have an animation that showing just the every cycle, not every tilt. Okay, just for fun, I'm just exploring this blindly, trial and error, playing with Wolfram language. But again, to properly solve the problem, you just need to think about this math. Like just sit there and think about this math issue. So is not just coding and see the pretty pictures, but let's see the pretty pictures. So now we want an animation where a cycle is each actual cycle tilt. Okay, so what you do is you list the moves. Okay, so now it's actually easy to do. This is not number of cycles. Okay, so so we can use the same data structure, but here instead of 4, let's see. So maybe that will do. Okay, try that. Okay, so now it should show slow down. So now it's showing the north, each cycle north. Okay, changes. So this is showing each 4 tilts. Just fascinating though. It's fascinating. You see, so if you each set of 4 tilts, they also have a periodicity. Okay. Oh fuck! You have to find the periodicity. Fuck. Oh, I get it. Now I know. You see, here's the thing. So you don't want to consider each tilt. Rather, you want to consider each cycle. Cycle here is defined as, north, west, south, east. This sequence of tilts. So you want to look at the cycle, right? Right now we are observing the effect of each cycle. Okay. So, but if you look at this, then you can see do they ever repeat? I think they do. Okay, so let's observe this pattern. Even visually, it's not so easy. Okay, so So I think, so if you look at the cycle and the result of each cycle, they repeat too. But they don't just become stable. Instead, they repeat. There's a period. Okay, so yeah, so there is a period. Tricky, very nasty, well, a good problem. Okay, so this advent of code, day 14, was it day 14, part 2? Okay, 2023, a good problem. So you want to know, basically, you want to find out the periodicity of this function. Oh God, that to compute that. Oh God, to compute that is not trivial though. It's not obvious. You want to find out the periodicity of this function. The function in question is this F1 cycle. Okay. So you want to find out periodicity so that so you don't call nest, nor do you call fixed point. Because if you just call fixed point, oftentimes they actually they never repeat neighbor by neighbor. They they never become stable, the pattern. But however, the pattern becomes stable in a sense that they repeat. So there is a periodicity. Maybe after 5 cycles it repeats. The same 5 frames, they repeat over and over again. It may be the periodicity, maybe 9, maybe 90, maybe 1,000,001. You don't know. But however, once you know the periodicity, then you know when the function is repeated n times, you know exactly what configuration it will be without having to compute it. So, if the question is asking for 1,000,000,000 repetitions, then if you know the periodicity is, let's say 100, then you just you just have to compute 100 times. You never need to compute more than the periodicity number of times. Okay, right. So you just need to know the periodicity and yeah. Oh, okay. So you need to find the periodicity of this cycle function. And the result, the result board configuration is basically the last step in that periodicity. Okay. Okay. I kind of got the idea. Okay, very tricky problem. Now let's look up documentation, fixed point, see if there is kind of some built-in option to detect periodicity. No. Okay, well, you got the same text. Okay, so actually you can use the same test. That is the key. You see, the fixed point is a function that computes a function with a given input. It will stop when the result no longer changes. Okay, then you can give a third argument that says do a maximum of n times. In our case, 1,000,000,000. But however, it won't work because each time you run the function f, in our case is the F1 cycle. Each time you run this function, the result will not be the same. Most of the time, it will not. In, in some, I guess no, they will not be the same. because you can see this tricky thing. Each time they run, they will not be the same. The ball will be moved somewhere. But however, they repeat. So you need to find, they repeat, okay? So you need to find their periodicity, like how many different board configurations they will end up. So you find the periodicity, then you can apply this same test. Okay, so let's see. The same test applies as to successive pair of results. Fantastic! That's exactly the solution. Okay, let's check some example. Beautiful Wolfram language, you see. They have thought out about this issue. When you have a fixed point, okay, well, the function doesn't repeat by itself. I mean, it never come out the same. However, the function may have a repetition, a cycle, a periodicity. So you just say, you just say same test and give a number. Let's see. Yeah, well, the problem is to find out, what is the likelihood, what is the range of periodicity? Options, same test there, okay? So stop as soon as successive iterations differ by less than that. Okay. Differ by less than that, okay. Successive iteration differ by that, no. What about this? Perform exact arithmetic but use a numerical comparison function. So no. So the same test is a function. Okay. It lets you specify. Okay. We need, right now we need a function that does repetition like fixed point, but however, to be able to detect the cycle. So let's see, Wolfram language, fantastic. You have so many options. Stability conditions, okay, let's look at some of them. R fixed point gives the fixed points for a recurrence equation. That looks like very promising. Recurrence equation. Okay, equation then gives the fixed points for a recurrence equation. Okay, so we need to turn this into an equation, or what is it? Oh God, this requires thinking. So we need to turn this function f1 cycle and express it as a equation. So, and f cycle, you need to also change it so it takes a number of times to repeat. That's easy. So we, for example, let's just play with Wolfram language. So I'm just okay. So for example, you want to let me do this. Okay, so you define f1 cycle n. That means repeated. Okay, let's say repeat. Okay, so you define that by equals to nest. Okay, so f cycle repeat. Okay, so let's use a function. Okay, so function. So it's a function. Then the body of the function. So xn. So the argument is is two arguments. One is x, then n. Then that means you call F1 cycle begin with x initial value and repeat it n times. How beautiful. This is how you do. So this F1 cycle repeat n, okay, so this defines, you run the F1 cycle n times, okay? So now this function, now you have to say, so basically if you want to use this, fixed point relation, recurrence equation, so you got the equation f repeat x then n is equals to, let's say the periodicity is 5, okay? Then it means then equals to n minus 5, something like that. So this is how you determine something like that, okay? Equation an and n gives the fixed points for a recurrence equation. So recurrence equation, wait a minute. You can't, that's not, F cycle is not a recurrence equation, no. Yeah, so I don't think you can do that. F1 cycle is not a recurrence function because it does not define what the function is in terms of the previous one. But what about this? So F1 cycle repeat n. Oh, yes, then you can. So repeat n, let me try that again. So repeat n equals to, yes, okay, so you can actually define this as a recurrence relation. F cycle repeat n just means F cycle n minus 1, okay? It equals to F cycle applied to F cycle n minus 1, there. So here we have a recurrence relation. However, now it involves two functions, so it's probably not appropriate. So we need to rewrite again in terms of one single function because this is involving two functions. Anyway, so that's, and this is new in 14.1. This is, then I don't think that's what we want because when it's very new, then it's less used. I'm not even sure I have it. I'm using undo, fucked up. So let's see, fixed. Yeah, I'm not using 14.1. I'm using 14. Yeah. So in order to know, you run $ version number, okay? Shift enter. Yeah, I'm using 14.0. So this is new and not likely what we want, but very fancy. And this is not experimental, otherwise you'll say. So this is there for good. But however, it's not likely what we want. So our stability conditions also new. Our fixed point, D fixed points also, also in 14.1, not likely what we want. what we want, you see, these are like differential equations and chaos systems, dynamical systems, and chaos theory, kind of. That's why they have these recurrence equations. That's what dynamical systems is about. Like you define a function in terms of previous time, time-based, like the flowing of water or stream, something like that. So that's not likely what we want. We want a function that determines the cycle of a function, like the periodicity of a discrete function. Okay, so you give a function f. Every time you call it, it returns something. You call f again on the result, then you call f again on the result. But f is such that after you run a few times, it repeats. You call itself, it starts to repeat, like 1, 2, 3, 1, 2, 3, 1, 2, 3. So you want a function that takes a function and determines the periodicity of that function. Okay, so that is what we want. Now we thought about this, and good, we got a clear understanding what is needed. So the question now is there a function in Wolfram language that determines cycle? Not I know of, not in my memory. So let's search and see if we can search for periodicity. Fuck, stupid English. PIOD. Let's do muscle memory. No, that doesn't. Fuck. Search. Let's just search. The city. Okay, that is actually how you spell it. Periodicity. DICITY. Period. What? Periodicity. God. Okay, anyway, let's just search for period and let's see what we find. Sampling period, geological period data, historical period data, function period plot. Oh, let's see, function period, find nest plot, find nest period. No, that's a resource function. We don't want resource function. Resource function means someone has written it. Oh, fuck. This is exactly what we want. So this implies there's no built-in function that does it. So this resource function means someone wrote this package, and according to the documentation, looks like exactly what we need. God. Why is that? So find nest period. Try to find the repetition period for nesting of a function. Exactly. Attempts to find the repetition period. Okay. Yeah, but this okay. So this one is written in 2019. By whom? Let's see. Richard Phillips. Okay, I don't know. I don't think I know the guy. Okay, but this function should be easy to write. Or I can, we can simply call this, the power of Wolfram language. You can actually, you just paste this code, it'll work without having to import anything. Just call resource function, find next period, then it'll work. Yeah, but that's using someone else's code. I could write this myself. Let's see, next while. Maybe, yeah, actually we can just call next while. So your next while, yeah, but it will take some code to write this, to create this find next period. This is exactly what we want. You can try to implement it using nest while, which will nest a function with a given condition. But the issue is that you don't know, you have to accumulate a list each time. You have to compare the previous, compare to see when it repeats. So yeah, well, we can do that, but now I'm tired. Yeah, so okay, in summary, let's give a summary. Molina says will tally work? Maybe. Yeah. Let's see the documentation for tally. Tally the elements in this listing or distinct element together with their multiplicities. Yes. Okay, it'll work, but indirectly, because first of all, you don't know what is a period, right? And you have to do this a billion times. Right now, we have no idea what is a period, but I assume it's pretty small, like 100, less than 1,000 probably, because this devious problem, this devious advent of code, the period, but we have no idea what is a period. It could be 1 or 2 to even a billion, not likely a billion, because we can assume they designed the problem such that if you don't know about the period thing, your program will run for years. So the period is actually probably something small, like 1,000 or 2,000. But still, we don't know exactly what is a period. So if we gonna use tally, it will be some kind of trial and error. You run it for 2,000 times, then you tally, then you get the multiplicities, then you get the idea of the, let's, why don't we try it instead of talking, we can tally. Okay, so tally, what you want, you just want this table. Okay, actually board history. Let's try. Let's see what we got. What? Wait, what? Tally list. Oh, okay. Again, it's a cycle issue. Wait, why does it not work? So tally A, B, C, I, C, B, A. So they group. Yeah, so it should work. But, oh, it does. You see this 4, you see this matrix repeated once, that's a unique configuration. But you see this matrix is repeated 4 times, this matrix is repeated 4 times, you see 4 times, So after we call tally, then we use the tally result if their multiplicity is repeated. So if we have a lot multiplicities that are the same, then that is the periodicity of the functions, probably something like that. So you see, we see a lot 4s here, then the periodicity is 4. You see, we see a lot 4s here. You see, so this configuration repeated 4 times. This configuration, which is different from that one, is also repeated 4 times. This configuration is again different, repeated 4 times. So the multiplicity 4 appears many times. So that means this the cycle of this is 4. The periodicity of this is 4. 1, 2, 3, 4. Like every 4 times it repeats. Okay, let's check. So yeah, okay, so let's see. So it should be every 4 times it repeats. It's hard to see. I mean, well, yeah, anyway, so the tally idea is not a direct approach, and even then you have to guess, so I don't think it's good. Yeah, so you really just have to implement this find nest period. Is there some better way? I thought there should be a built-in function, because finding the period of function of a discrete function is fairly common. And then we have to look up his actually, so let's play with it. Let's actually we can do this. We can get the source code. Like, let's just try it. Okay, so it's so he's resource function, let's say fff equals to this resource function, shift enter, it'll go over the internet and grab that function. Okay, take a while. Okay, there we have it. Now question mark and FFF. Now let's see the definition. Okay, so and then you click on, okay, so you click on that, and that gives you the documentation. We want the source code. So what is this? You click on that. There it is, the source code. Beautiful. It's so convenient. So you can see the source code. Let's magnify. So we are cheating. We are looking at someone else's. But you see, yeah, you see, it's starting a guess 100,000 times as a guess for the periodicity. Because to do this, you need to, and also look at, he's using nest while. So basically, every time you compute this function, you have to save the result, then compute the next nesting, then save the result, compared to if it repeats any of the saved results. So then you have to try this initially 100,000 times. So basically, you are just you just have to save the result and try it each time. So let's see, block. Okay, so width, then if statements, then length. Okay, so no, I don't want that. Yeah, it's kind of yeah. Okay, so this will give you periodicity, but which is what we want. So once we know the periodicity, we have so let's say the period is 9. That means the F1 cycle has 9 distinct configurations for the board. Then if you want to do 1,000,000 times or 1,000,000,000 times, you take the mod of the billion over the periodicity. So billion divided by 9, you get a remainder. So let's say, what is it? Remainder is 1 in this case, something. But let's say the remainder is 3. Then you just take the third part of the period, the third configuration. That is the answer. Yeah, that's so simple. Now it's so simple. So now you want to find the periodicity of this function f cycle, right? Yeah, you want to find the periodicity of this F1 cycle. Let's say it's 9. Then to repeat this 1,000,000,000 times, you mod. Let's try it. Let's write it out, okay? Let's just pretend this works, okay? Copy. Periodicity equals to, call that function. Let's make it full. Let's just make it actually work, okay? So let me try this, okay? Cut, and do it properly over here, okay? Tally we don't want, fixed point we don't want, okay? And this we want, okay? Put a line break, and okay. And this will define, x find nested period, okay? So we define that function from this resource, okay? Then we define periodicity. We don't want that anymore. So periodicity, x periodicity equals to find the period of our F1 cycle function. And it requires an initial input, X matrix, and it also requires an optional try, okay? Optional try, okay, 100,000. Let's say, okay, let's just run it. Actually, this will give us answer. Run it. 1. Okay, 1 is not correct. What? The period of 1? Okay, so maybe we didn't try enough. Well, you shouldn't return 1. Okay, let's try 10,000. Okay, so Shift Control D break and Shift Enter 1. Did we call this function correctly? F expression n. F expression n. Why does it return 1? If the period is not found, find next period, return a failure object, okay? Yeah, but it returns 1 that means our function f1 cycle has a period of 1, which means it repeats every, it just repeats, return the same result, which is not true. And what is going on? Yeah, what's going on? Next list f1 cycle. So this is the first result, and this is the second result, and they are not the same. So why do you say period is 1? Ah, God, frustration, frustration, one after another. Or is it because, you see, that one of the problem is, you see, this resource function, someone else wrote it. So you have to trust this guy, Richard Phillips, is a great coder. But however, the Wolfram research function repository, they are curated, meaning that everything you see, as long as they are on Wolfram function repository, they are verified to be correct, at least in some way. So there's quality assurance. Otherwise, they wouldn't be on Wolfram function repository. That's by design. So every function uploaded there, as soon as if you can use it, that means it's at least 99.9 correct. Okay. So I should think that this function is correct, that we are calling find next period. But however, it's giving us 1 for the f1 cycles, which does not seem to be correct. So I used it wrong or something, because the period is not 1, because each time you call, they return different answers. So what is this tally? Okay, let's remove this tally, too big. So again, looking back at this f1 cycle, you see the period, you see this board history. Where does board history come from? Board history came from applying this function every 4 times. Oh God. So okay, I don't know, fuck, but we are getting close though. We're getting pretty close. Right now I just want to verify, why does this give us a period of 1, which does not seem right. Yeah, and okay, I think maybe that's it today. So we did 2 hours plus. Okay, yeah, good point. Not necessarily every 4 times. Yeah, okay, so I think we stop here. This problem is kind of nasty, but so far we do know, I'm pretty sure, I'm 99.9% sure that you need to find the periodicity of this cycle function. Then, the solution is, the whole solution is just, so once you know the periodicity, then you just 1 billion times 10 raised to 9, you do a mod, so modular arithmetics, so that divided by x periodicity, okay, that's a number. Then you just call nest, okay. Let's mark up the function solution. You call this function with the okay, so you call this function with the initial input of a matrix, and you call this number of times. Okay, so let's see. So that is the final board condition. Once you got the final board condition, let's write it out. Something like that. Final board condition equals to, okay. Then once you got that, then you just tally you just count there. Okay, so actually, so then you just do that and that should be the answer. Okay, so the new code would be just this, and we are calling someone else's function. Try to find the periodicity, and it's giving us 1, which is very weird. So we have to figure out what's going on there. Then once we got periodicity, then it's just final board condition is mod divided by periodicity, take the remainder and nest it that many times, then just total. Okay, yeah, but okay, that's it. Thank you guys for watching. Anything else interesting? Bye guys for today. Hope you enjoyed the show. Hope you learned some Wolfram language tricks, or some, or have some fun watching me solve this problem. If you like my stuff, go to xarli.info, XAR code at the bottom. Donate to me, Patreon or Amazon gift card or PayPal. Okay, thank you guys. Bye. So we shut down in 2 minutes or so. Oh, Steve says, great live stream today. Thank you, Steve. Steve, get on YouTube. Get on YouTube and bye guys. Hey, damn it, damn sick. Bye guys.